Okay, so we start with lecture 2. Last time we already defined a generalized inverse. Let's recall. So definition. We have a matrix A with m rows, mn columns. And we say that G, a matrix G, which has n rows and m columns. So recall that we switched the number of rows and columns. So G is a generalized inverse of A. If we have this equation, AGA is equal to A. So if we have a square matrix which is invertible, then G is just the usual inverse, because the usual inverse satisfies this equation, and it's the unique matrix which satisfies this equation. This is seen just by multiplying the equation from the left and from the right side by the inverse. However, for rectangular matrices, a generalized inverses are not unique. That's why here we have a generalized inverse and not the generalized inverse. We will also show that generalized inverse of a matrix always exists, and we will also write an algorithm how to compute it. So there is not a unique way to do it, but we will see how to do it. So let's first, to warm up, just prove this fact, which I've already mentioned, that for a square invertible matrix, a generalized inverse coincides with the usual inverse. So proposition, if A is a square matrix which is invertible, then G is equal to the inverse of A. So it's unique and it's equal to inverse of A. Proof. So I will write this condition AGA equals to A with 1. So how to prove that if A is invertible, then G has to be the same to its inverse? This is easy. We just multiply this equation 1 by inverse of A from the left to get rid of this A on the left, and by A inverse from the right side to get rid of this A. And on the left side, we will get only G. And on the right side, we will get precisely inverse of A. So, and this is the end of the proof. So we just multiply 1 from the left side and the right side by A inverse, and get so A inverse A, G A inverse. This is equal to, so this is identity, this is identity, so this is just G. And on the left, on the right side, we get A inverse, A inverse. But A inverse A is again identity, so we get A inverse. And we have that G and A inverse are unique, are the same. Okay, and let's now prove that a generalized inverse for any matrix, not only square matrix and not only invertible matrix, always exists. So proposition, or we can say theorem, because it will be important for us in the continuation. So A is a rectangular matrix with n rows and m columns. Then a generalized inverse, its generalized inverse exists. Then its generalized inverse G with m rows and n columns exists. Since we are in the mathematical modeling course, we're not only interested in the theoretical result, but to work with a generalized inverse, we would like to have a constructive proof. So we would like to have a proof which in fact constructs this G, because this will enable us to then calculate with this G. So the proof of this theorem will be constructive. We'll write explicitly what one of those G looks like. So first, let's define R to be the rank of A. So this R in particular is smaller than the minimum, is smaller or equal to the minimum between the number of rows and the number of columns. So this R is at most minimum between n and m. But it can be even smaller. And we will separate two cases. One will be more clear, and the other will be just a technical reduction to the first case. So let's start with this clearer case. Case 1. Let's say that the rank of A is equal to its left upper corner, so left upper R times R submatrix. So rank of A is equal to rank of A11, where we decomposed A into this form. So A is equal to, we have two by two blocks. So it's 2 by 2 matrix of blocks A11, A12, A21, and A22. And here we have R columns. Here we have the remaining number of columns, which is just m minus R. And then here we have R rows, and then the remaining number of rows, which is n minus R. So, and this case 1 assumes that this left upper R times R corner of A is in fact of full rank. It's square and it's of full rank. And I ask you what would be the claim about the generalized inverse of G. So we claim that G is equal to, and now I ask you what you think, what would be the candidate for G, and then we will also prove that this is really the appropriate candidate. So what would be the first guess about this G? So this A11 is invertible. In the last proposition, we said that the generalized inverse of an invertible matrix is unique, and it's just its usual inverse. So if we take this into account, we would say that in the left upper corner of G, we expect to have an inverse of A11. So we expect that here we have A11 inverse, so usual inverse. And what about in the other three entries? What would be the easiest guess? So let's try with the trivial matrices, so 0, 0, 0, and we will then correct if necessary. So we claim that G is a candidate for a generalized inverse. And let's write generalized inverse by GI to shorten the notation for a GI of A. So what we have to check? So how would we prove that this G is really a generalized inverse of A?
We can multiply A with GA.
Yeah, that's true. Yeah, we have to check that AGA is equal to A. And let's do this calculation. It will be mostly trivial, but there will be only one non-trivial part at the end, which we'll have to argue about. So let's do this calculation. So AGA is equal to, and this is easy to check that we have the composition of a matrix into blocks, and those blocks are appropriate sizes. Then we can compute with those blocks in the usual way, as if these blocks would be scalars, so real numbers. So it's easy to check that we can do this in the same way as usual matricial computations, so matricial multiplication. So we have A11, A12, A21, A22, and then we have this G, A11 inverse, and zeros, and again A. Now we do this calculation in two steps. First, we calculate, we multiply these two matrices, and what we get is a matrix. So A11, A12, this row is multiplied with this column. So we get just A11, A11 inverse plus A12 times 0, so it's 0. And then the second row is multiplied with this first column, and we get A21, A11 inverse. But in the second column, there are only zeros. So whatever row we multiply with this column of zeros, we will get zeros. So first row times the second column is just a zero matrix, and the same for the second row and the second column. Okay, this is the first multiplication, and then we have to multiply this matrix with A. So I only wrote here this A again, and I will calculate here. So again, first row, we can already notice that this is identity because we have A11 times inverse of A11, so this is identity. So when we calculate first row times first column, we get A11. And then first row and the second column, we get A12. And here, we have second row and first column. So we get A21, A11 inverse, and A11. Okay, let me write this A12 a little bit more to the right side. Okay, and then second row and second column, what we get is A21, A11 inverse, and A12. And let's recall what we want to show. So we want to show that this is just A. So we are proving that this is just A. So if this is true, then this computation, this matrix, should be equal to A, which is A11, A12, A21, and A22. And now we compare the corresponding entries. So we have A11, A11. This is okay. Then we have A12, A12. This is also okay. Then here, second row, first columns are also the same, because here we have that A11 inverse A11 is just the identity. So for those three entries, the computation was trivial. And now we come to the non-trivial part. So the second row and second column compared to the second row and second column of the computation don't look to be exactly the same at first sight. So we have A22 equal to A21, A11 inverse, A12. So we have to check that this equation is also true. And now there might be two possibilities. Either our candidate for the inverse was not correct, or we didn't use all assumptions. So we should use some other assumption to show that this is true. So does anybody have an idea what to do? So do we have to change our definition of G, or do we have to take into account another assumption which we didn't? And which assumption is this? So what assumptions did we have? So our assumption was that the rank of A is equal to the rank of A11, where we have this block decomposition. And we only use that, from this case, we only use that A11 is invertible. So if rank of A is equal to rank A11, then rank of A11 is invertible. Then A11 is invertible. And based on this, we claimed that G should be of this form. However, here we didn't use any assumption on rank of A, because if rank of A is equal to rank of A11, then we know that these columns, the columns of A12 and A22, are in the column space of the columns of A11, A21. So this is one assumption which we could also use, and we didn't use it anywhere in our calculation. So let's try to use this assumption and see that we indeed have equality here. So rank A is equal to rank A11 implies that the second column, so columns from the second block decomposition of A, which is A12, A22 belong to the column space. So every column of this submatrix belongs to the column space of the submatrix A11, A12. So if the ranks are the same, then this has to be true. And let's recall from the last time. So we said if you have matrix A, then so a vector U belongs to the column space of A. So this is a vector, and this is a matrix. So if and only if this is true, if and only if there is some vector V such that AV is equal to U. So in other words, this equation says that some linear combination of the columns of A is equal to the vector U. So the only difference between this claim from the last time and the claim here is that this column is not actually a vector, but it's in fact a matrix of vectors. And for each column of this matrix, we know that there is some vector V such that A11, A12, V is equal to the corresponding column of A12, A22. And what we do, I see one question in the chat. Okay, thank you. Yeah, here is in fact a mistake in the index. So it should be A21 here. A21. So what I wanted to say is that we use this claim for every column of this submatrix A12, A22, and for A we take our matrix A11, A21, and what we get that A12, A22 is equal to A11, A21 times some matrix. So in this matrix U consists of the vectors U1 up to U m minus r. So let's write this. In a more concise way. So let's write this in the column notation. So we have here vectors U1, U2 up to Um minus R. And from this claim, we know that for each of these UIs, there is some vector VI, which this matrix A11, A21 maps into UI. And so we just collect them into a matrix. So we have here V1, V2, up to VR, because this Vm minus R, and this has R rows, R columns, and M minus R and n rows. And so this v1 is this v1 up to vm minus r are, so here we have m minus r columns, and here we have r rows. So we have a12, a22 is just a11, a21 times some matrix V. Which means that a11 V and a21 V is equal to a12, a22. And now we will just express, so what we want to show that a22 is equal to a21, a11 inverse, a12. So we will just, from these two equations, we will just get rid of this V. We will express V with all the other unknowns. So from the first equation, what we get from the first equation, we get that a12 is equal to a11V. And from the second, we get that a22 is a21V. And what can we do now? How to get rid of this V? So from this first equation, I see answer in the chat. Yes, that's true. So we just multiply the left side of this first equation by the inverse of a11, which we can because we know that a11 is invertible. So we have this, let's say, 2 multiply 2 with inverse of a11 from the left. Side, and what we get is a11 inverse, a12 is equal to, and on the right side we get a11 inverse, a11 V, but this is just identity times V, so this is V. And we plug this into 3, so this is 3. So we plug this into 3 and get a22 is equal to a21 times, instead of V, we plug the left side, so a11 inverse, a12. So this is what we could extract from the fact that rank of A is equal to rank of the first R columns, or even the first R columns and the first R rows. And this is just the last equation which has to hold for our generalized inverse to be of the form we claimed. So this proves what we've checked, proves this last equation, which means that our generalized inverse is again really of this form. So we just invert the left upper block and put zeros in the other blocks. And of course, the dimensions are then, so those zeros are of appropriate dimensions. So recall that if A was n times n matrix, then this G must be m times n matrix. So if inverse of A11 has R columns and R rows. And that means that here we must have n minus r columns and m minus r rows. So those zeros are of appropriate dimension. Is there any question about this case?
So first we have to find the rank of A, and then we can find the inverse of this A11. So that's how we get G.
Yes, that's true. Yeah.
Okay, thank you.
That's true. But for now, we only covered the case when this rank is in fact reached in the left upper corner. And the other case which remains is the general case. So it's not necessarily true that rank of A will be the same to the rank of A11. It could be that we should use the last columns or some middle columns or something like that. But we will just translate this second case into this first one. And then we will write the algorithm, how to do this in general, and also calculate one example to see how this works. So this was case 1. And we have case 2. Rank of A is not equal to rank of A11. What to do in this case? So one way, so we have, let's visualize the situation. So we have A. We know that its rank is R, which means that there are R columns which are linearly independent. And let's say that these are this column, this column, this column, and so on. They are not the first R columns. And within these R columns, so this is 1, 2, 3, so on, R. Within those R columns, there are rows which are also linearly independent. So let's say that this one, so we just intersect these R columns with R independent rows. We have 1, 2, 3, and so on. And what will be the candidate for A11? So in the first case, those violet columns were the first R columns, and the green rows were just the first R rows. But here it's not the case. This is not the case. So what would be the candidate for A11 in this case? So just the intersection of those rows and columns. So this would be the candidate for our A11. So A11 is a R times R submatrix which is invertible. And what would be then the candidate for G? Then G, the candidate for G, so basically the same idea, only that it's a little bit more messy to write, because now we have in the corresponding, so it's easier to see than to write. So on those places of A11, so we just invert A11. So let's write in Word. So So we calculate the inverse of A, 1, 1. And then plug A11 minus 1. And here is a little bit technical thing. So A11 minus 1 transpose into the entries of A11. We put zeros in the other entries. And then we just transpose everything. We transpose the matrix. The matrix formed in 1 and 2. So here we have the entries. So we have A11. This is the submatrix in this black point. We invert it. We put it, so then we calculate, so we invert it and then we transpose it, put it in these corresponding points in the submatrix A, then put zeros everywhere in every other entries, and then transpose everything so that we really change the number of rows and columns. And this is also the reason why we have here transpose, because in the third point, in point 3, we transpose again. And if we transpose twice, then transpose cancels out. So this transpose here is nothing else but because of changing the number of rows and columns at the end. Otherwise, it doesn't have any real reason why it has to be here. And this is basically the same calculation as in case 1, only that it's a little bit more messier because we have to be careful when we do the computations. But there is also other way, which we are not going to thoroughly look at, but it will be in your handouts. So the other way is what to do to transform this into case 1 is just multiply A by some permutation matrix from left to change, to swap rows, and by some permutation matrix from the right side to swap columns. And we use such permutation matrices that these black points, in fact, become the left upper corner of this permuted matrix. Then we use case 1. And at the end, we again use permutation matrices, P and Q, so that we again change rows and columns in the appropriate order. So it's a little bit technical, so we won't go through this, but you can also look in the handouts. So to finish this this first hour, we'll just extract the algorithm for computing a generalized inverse of A out of this proof. So let's say that this proof is finished, and we extract the algorithm for computing a generalized inverse of A. And then we will do an example after break. So R is the rank of A. And in the first step, we find a non-singular matrix we find a non-singular matrix. So non-singular submatrix B in A of order R times R, or of size R times R. This was A11 in our proof. So in case 1, it was just the left upper corner, and in the case 2, it was some submatrix, some R times R submatrix. And what we do, so in A, substitute, this is what we did in the second case. So elements of B for the corresponding elements of B inverse transposed. All the other elements with zeros. And at the end, we have to transpose everything. So the transpose of the matrix from 2 is a generalized inverse G of A. And let's only comment on this algorithm. So even from this algorithm, we see that there are many ways to calculate the generalized inverse, because the choice of a submatrix B is non-unique. So any non-singular submatrix of order R times R, where R is a rank of A, is a good choice. And it gives us some generalized inverse of A. So to conclude the first hour, are there any questions?
Yes, so unless A is a square matrix, there are more than one generalized inverses.
Yes. Yeah, that's true. And we will also see another way how to see that there are more generalized inverses. So one way is just to follow these steps in the algorithm, and we see that this step 1 is non-unique. Any non-singular submatrix of order R times R is appropriate choice, and it will give different construction at the end. But there will be also other ways to see that there are more inverses, which we'll shortly reach in the second hour. And there is also a complete characterization of all generalized inverses of A. But we won't go into this. But there exists. They can be described by a formula. Maybe some other question? So let us proceed. Only to answer the last question in the last hour. So yeah, this algorithm mostly proves that there are more generalized inverses. Whenever the choice of this submatrix B is non-unique, we get different generalized inverses using this algorithm. However, there is one case, so it could be, there is one trivial case, so it could be that this submatrix is unique. This would be the case when we have, for example, matrix A, 0, 0, and this has R rows, R columns and R rows, and rank of A is R. So for this matrix, you see that the choice of B in the algorithm is unique. So we need to choose exactly this upper left corner for B in the algorithm. So our algorithm only gives us one generalized inverse. And this is exactly, so algorithm gives us G is equal to A inverse 0, 0, 0. But AGA, but let's look at computation A 0, 0, 0. This is our big matrix. And then here we have this generalized inverse, A inverse in the left upper corner. So we have here A 0, 0. And the result must be A 0, 0. So the algorithm says that we have zeros in those remaining entries, and this is one of the generalized inverses. However, we can notice that what we have here in the bottom row, in the bottom matrix row, doesn't have any impact on the calculation. So what we plug in here, so B and C, only here we must have 0 because in this entry we are computing A0 and so first row multiplied by this column, and this A gets multiplied by what's here. So here we must have 0, otherwise it will appear in the calculation on the right side. But this B and C immediately vanish already at the first computation. So we here multiplying these two matrices, we get identity 0, 0, 0, no matter what B and C are. So there are many generalized inverses. So B and C are arbitrary in this case. But there are also other ways to see that generalized inverse is non-unique. Okay, and let's do one example to see better how this algorithm works. So we take A to be 3 times 4 matrix equal to 0, 0, 2, then 0, 0, 0, 2, 1, 1, 0, 0, 4. And we will calculate generalized inverse of A. So first, we have to determine what's the rank of A. And since there are less rows than columns, it's easier to look, to observe the rows and see how many of them are linearly independent. So if you look at the first row and the second row, we see that the first is just 2 times the second row. So the first 2 rows are linearly dependent. So we can take only the first row, forget about the second, and look at the third one. And yeah, the third one cannot be expressed only using the first, or vice versa. So the first cannot be expressed only using the third. For example, here we have 2, here we have 0. So the third must be multiplied by 0 to get the first, but then in the third column, the numbers won't match. So rank of A is 2. And by the algorithm, we have to find a 2 by 2 submatrix B of this A and do the calculations with this B. you can choose your own B. There are more choices. For example, so we are searching for 2 by 2 invertible B. One of the choices is this submatrix. So it's easy to see determinant is 1 times 4 minus 0 times 1. So determinant is 4. This matrix is invertible. So this is one choice of B. We could also choose some other matrix, for example, this. Also, this one has determinant, non-zero determinant. So it's 0 times 1 is 0, minus 2 times 2, it's minus 4. So this is also appropriate choice. And both of them will give us different generalized inverses. So let's do the calculation with red B. So we have to calculate. So first we choose B is equal to this lower right submatrix 1, 0, 1, 4. Now we have to calculate B inverse. Okay, since this is a 2 by 2 matrix, let's do this calculation. It will be very short. So one way is to write our matrix B on the left side and then identity on the right. And by Gaussian elimination, achieve after row multiplication and row subtraction, that on the left side we have identity. So what we do, we can subtract the first row from the second and get, so first row remains the same, and we subtract from the second, so we get 0, 4, and minus 1, 1. So here what we did was the second row is the second row minus the first row. And we only need here to multiply the second row by 1/4 so that we will get 1 on the diagonal. And we do this and get 1, 0, 1, 0, and 0, 1, and minus 1/4 and 1/4. So we have here second row is all second row multiplied by 1/4. And so this is B inverse. So minus 1/4 and 1. Yeah, thanks. Yeah. Here I did a mistake, so it's 1. No, it's 1/4, yeah, because we have to, so we multiply the whole row by 1/4. So even this minus 1 becomes 1/4, and also this one becomes 1/4. So it should be correct. Okay, and so what we do, so B inverse transpose is then, so this is B inverse. B inverse transpose is then 1 minus 1/4, and then 0 and 1/4. And we said that we plug this into the corresponding place of B. So we plug here B inverse transpose. And on all other places, we have zeros. So in the third part, we just plug here in the right lower corner this B minus 1 transpose, 1 minus 1/4, 0, 1/4. And on other places, we have zeros. and transpose everything. And this is our G. So we have 0, 0, 0, 0, 0, 0, 1 and minus 1/4, 0 and 1/4. So you see that this B inverse, in fact, occurs. B inverse occurs in the right lower corner of G. So you see that this transpose only has to be done because then we transpose everything again. So if we do this, if we already know in advance that G, what will be the dimensions of G, then we don't need to do transpose twice. Just put inverse of B on the corresponding entries of G and fill other entries with zeros. So this transposing is only to match the dimensions of G. So it has to be, so if A was 3 times 4, then G must be 4 times 3. And let's check if this calculation was okay with MATLAB, I mean with Octave, to make sure that there wasn't a mistake. So our A was 0, 0, 2, 0, and then 0, 0, 1, 0, and then 2, 0, 1, 4. Our candidate for G, if the calculation was correct, was 0, 0, 0, then 0, 0, 0, and then 0, 1, 0, and then 0 minus 1/4 and 1/4. And what we have to check that A times G times A minus A. So AGA is A. In other words, AGA minus A must be equal to 0. And yeah, so we see that we really get zero matrix. So this G is one of generalized inverses of A. And we will need this example shortly when solving linear system. And we will do this on the same, for the same matrix A. Okay, this was one example of calculating a generalized inverse so that we see how the algorithm works. And now comes the basic theorem for generalized inverses, and this connects. So this theorem will connect solving our system A, X is B with generalized inverses. So we have this theorem. A will be again n times m matrix. B will be a vector from r to the power of m. And now we assume that the system A, X is B solvable. So if the system A, X is B is solvable, so recall that this means that B belongs to the column space of A. Then X is equal to GB is one of the solutions of this system. I will write it with 1. So it's one of the solutions of 1. So here, where G stands for a generalized inverse of A. So this is the same as as is the case in the square case. So when we have a square invertible matrix, then the solution of this system is just inverse of A times B. And in this case, we prove that inverse of A corresponds to coincides with a generalized inverse G. When A is not square matrix or when A is not invertible, then this has to be adapted a little bit. So instead of inverse of A times B, we have to take any generalized inverse G of A times B. But this is only one solution of this system. However, we can describe all solutions of this system. So moreover, all solutions of one are exactly vectors of the form x, so xz xz is equal to g b. So this is one particular solution. And then we can also add something from the kernel of A. So if GB is one of the solutions, and then we add something from the kernel of A, then this is also a solution of the system, because something from the kernel will be annihilated by A. So we won't change the right side. So here we could add anything from the kernel, but we don't need to compute the kernel, because the theorem says that the kernel is precisely GA minus an identity times Z, where Z is any vector from R to the power of M. So one of the solutions is this GB, while all solutions are GB plus GA minus identity Z, where Z varies over any M tuple of real numbers.
Where did we get the GA minus identity from?
We will prove this shortly. So we will prove that this GA minus identity Z is exactly the kernel of A. So we will see from the proof. It's not clear. It's not clear from the statement why we get exactly GA minus identity times Z here, but it will be clear from the proof. Okay, so let's prove those three facts. So first thing, we prove that GB is a solution of the system 1. So this is the first thing which we are going to prove. So let's write A in the column decomposition. So A is the same. So A in the column decomposition is A1, A2, up to AN. So let A be the column decomposition of A. This is just notation. And now we know that B, since B belongs to the column space of A, since the system 1 is solvable, it means that B belongs to the column space of A. And this means that there exist alpha 1 up to alpha n real numbers. sorry, here we have m columns. So n is the number of rows and m is number of columns. So there exist alpha 1 up to alpha m real numbers such that we have linear combination of a's, and alpha i's are the coefficients, is exactly b. And let's denote this by 2. So I only wrote what means that b is in the column space of A. So there are some real numbers such that the linear combination of the columns where the coefficients are those numbers is equal to b. And we have to somehow introduce GB into our calculations. So what would be the way to introduce GB into our calculations? So how to get GB from this equation 2? We can just multiply everything by G from the left. So multiplying two by G from the left, we get, so on the left side we get sum of vectors alpha I acted, so and then G AI is equal to GB. So now we introduced GB into calculations, but we want to show that AGB is equal to B. So we want to show that GB is a solution of our system. So we want to show that AGB is equal to B, because we are solving the system AX is B, and we claim that X is equal to GB is one of the solutions. So this is what we want to show. So we have to somehow introduce AGB into our reasoning. And again, what we can do with this equation 3, we just multiply it by A from the left, and we will get AGB on the right-hand side. So multiplying 3 by A from the left, we get, so we get I goes from 1 to M, alpha I, AG, AI is equal to AGB. So this is true because 2 was true. We multiplied 2 by G, we got 3, so 3 is also true. And now we just multiplied 3 by A and we got 4, so also 4 is true. But our goal is to prove that AGB is equal to B, and this AGB is the right side of 4. So what we have to check is that the left side is equal to B. So we want to show that the left side is equal to B. And if we are able to prove this, then we prove that GB is a solution of AX is B. So whenever I use underlined dotted line, this means that this is not, this is something which needs to be checked or proved. so far we have never used the fact that G is a generalized inverse of A. So we have to use somehow this assumption that G is a generalized inverse of A. And here is the appropriate time to do this. So we know that AGA equals to A, or in the column notation, we can write AG, and for A, we use this column decomposition, A1, A2, up to AM. This is equal to A1, A2, up to AM. Or writing this in the vector way, or this is further equivalent to AG A1 is equal to A1. So AG on the first column is the same to the first column of the right side. And then AG on the second column is the same to the second column of the right side. So AG A2 is equal to A2, and so on. AG AM is equal to AM. So I only rewrote this equation into M vector equations. And now observe the equation we want to check. So let's write it as with 5. And we see that on the left side, we have those AG, AIs. But what we just checked is that AG, AI is equal to AI for every I. And we can use this into 5. So using star in 5, we get that 5 is equivalent, to sum of, so I goes from A1 to M, alpha I times, then with, instead of AG, AI, I write AI, is equal to B. So 5 is equivalent to this equation. And what to do now? So we are checking that 5 is true. And we prove that 5 is true if and only if 6 is true. Because 5 is equivalent to 6. So what we have to do now? Do we maybe know that 6 is true from somewhere else?
6 is the same equation that we had as 2.
Yes, that's true. Yes. So we started with 2, which is true. Then multiplied by G got 3, multiplied by A got 4. So 2, 3, 4 are all true. Then 5 was something to be proved. But 5 is equivalent to 6. But 6 is just 2, so it's true. So since 6 is equal to 2, it holds. And this proves that GB solves our system 1. Are there any questions at this point?
Yes, why can't we just say that AG is identity in phi?
AG. So why can we say that AG is identity?
Yes.
So because AG is identity only if A is a square matrix and G is a square matrix. So if we look at the example above, we had A. So this was our A, which was of rank 2. And we calculated G, which is also of rank 2. And then AG. So AG is a matrix which has 3 rows and 3 columns. And it is of rank 2 because if you multiply matrices, then the rank cannot increase. The rank of A times G is at most minimum between the ranks of A and G. And rank of A is 2, rank of G is 2. So also rank of AG is 2. But AG is a 3 by 3 matrix, so it must have a kernel. So AG is not identity. So AG is identity only on this 2 by 2 subspace of R to the power of 3. But then it also has a kernel.
Okay, thank you.
Thank you for the question. So yeah, we have to be a little bit careful when dealing with generalized inverses. Okay, so GB solves our system. And what remains to be checked is that all the solutions are of this form. So one of the solutions is this. And now we can add something. And this something is exactly GA minus identity times some vector Z to get Z to get another solution. And let's prove this fact. So second step, all solutions of the system 1 are of the form xz is equal to GB plus GA minus identity Z. So there are two things to be proved. The first thing that we will first prove that every xz is a solution of 1. And then the second fact will be that if x prime is a solution of 1, then x prime is xz for some z. So one of these steps is really trivial. One is just computation. This is the first step. So to check that every xz is a solution of 1, which is just one line computation. So I is trivial. So we have A on xz. This is A on GB plus A on GA minus identity times Z. But we've already proven that AGB is equal to B because GB is one of the solutions. But here we get, for the second vector, we get AGA minus A times Z. But we know that since G is a generalized inverse of A, we know that this is A minus A, so it's 0. So this is then B plus 0, which is B. So I really follows from the short computation. And now let's check II. So let's say that X prime is a solution of 1. So we know that since X prime solves 1, this means that AX prime is equal to B. But on the other hand, we also know that AGB is equal to B. And if we subtract those two systems, I mean those two equations, we get, so subtracting, we get that A of AX prime minus GB, this is left side, is equal to B minus B on the right side, but this is just 0. So what can we infer from this equation is that X prime minus GB is in the kernel of A. So this means it follows that X prime minus GB is in the kernel of A. So this means that X prime minus GB is some vector V, where V is in the kernel. Which means that X prime is equal to GB plus V. And of course, V is from the kernel. So we want to prove that X prime is equal to GB plus GA minus identity on some vector Z. But now we prove that X prime is GB plus some vector V from the kernel. So it follows that it remains to show that V is equal to GA minus identity times Z for some Z in the kernel of A. So this is the only thing which we need to prove. And does anybody see what to take for Z?
But why does that have to be in kernel?
This V, because X prime minus GB is in the kernel of A. So we had here AX prime is B, then AGB is B. We subtracted, and we got that A on X prime minus GB is 0. But this is just the definition of the kernel. So this X prime minus GB is a vector from the kernel of A. And we just denoted this vector by V. And
yes,
we are proving that this V is then of this form.
Yes, but why does Z have to be in
Oh,
kernel?
sorry. Yeah. So Z is any vector from R to the power of M. I already knew that it will suffice to take it from the kernel, but it's any vector from R to the power of M. Yeah, thank you. So what would you take for Z? Does anybody see? It's very connected with V. It's almost V. We only need to correct the sign. So if we calculate GA minus identity on V, we get GA V minus identity on V, but we know that V is in the kernel, so this GAV will disappear, and we will get minus identity on V. So the signs won't match. We only need to check to change the sign, and taking Z equal to minus V, we get GA minus identity on minus V. This is equal to GA, so minus GAV, and then minus identity on minus V is V. And this GAV, since V is from the kernel, is equal to 0. So here we use that V is from the kernel of A, and we got V. So this proves our theorem. Was this clear? And it's a good way to finish this second hour by an example. It will be short because we already have the machinery from the last example. So let's demonstrate the last theorem on the example. So we have solve AX equals to B, where B is equal to 214, and A is, as in the last example, so it's 0, 0, 2, 0, and then 0, 0, 1, 0, 2, 0, 1, 4. So first we have to use the theorem, we have to know that B is really in the column space of A. But it's easy to see because here we have B is 214. So it's just the third column, 211, plus some multiple of the first column. So plus 3 halves of the first column. We could also try to compute GB and check that A GB is really equal to B. And if AGB is not equal to B, then we know that this system is not solvable, because if it was solvable, then the solution, one of the solutions would be GB. So one way is just to check, to calculate GB and to check that AGB is really B. This also implies that the system is solvable. So we know from before, from the last example, that G is equal to, so we had 2 rows of zeros, and then we had 0, 1, 0, and 0, minus 1 quarter, 1 quarter. Okay, let me write also those zeros so that it will be clearer. And then we calculate GB. We won't do this by hand. So GB, you can do this in Octave, and GI minus identity are, so the first is, in fact, it's easy to calculate GB by hand. So it's just 2 times, so 2 times the first column of G plus 1 times the second column of G plus 4 times the third column of G. So we get 0, 0, and then we have 1 and 3/4. This is B, this is GB. And then GI minus identity becomes a 4×4 matrix, -1, -1, and here 1/2. And everywhere else we have zeros. And what theorem says that then all solutions are x z is equal to GB, so 0, 0, 1, 3/4, plus this GA minus identity on any vector z from r to the power of 4. So Z1, Z2, Z3, Z1, Z2, Z3, Z4. And if you calculate, you get, so we have minus the first, so the first row of GA minus identity times the column of Zs becomes minus Z1. Then the second row of GA minus identity times Z becomes minus Z2. And then the third row of GA minus identity is just 0. So we don't have anything because of this second summand in the third row. So in the third row, it must be the third row of GB, which is 1. And then in the fourth row, we get 3/4 minus then fourth row of GA minus identity times Z, which is minus 1/2 Z1. And Z1 and Z2 are parameters. So Z1, Z2 belong to real numbers. So we have a two-dimensional set of solutions. So the set of solutions is two-dimensional. Okay, this would be all for the second hour. Maybe now, any questions? Okay, if not, then let's do a break, 15-minute break, and then in the third hour, we will study one special generalized inverse, which is in fact unique. So we add few conditions and get uniqueness of the generalized inverse, and this will be the Moore-Penrose generalized inverse. And it will be especially important when solving systems AX is B, where the solution, the exact solution won't exist. So this Moore-Penrose inverse will help us to solve the solution by the method of least squares. Okay, so what we did in the first 2 hours is defined or recalled the definition of a generalized inverse, proved that generalized inverse of every matrix exists, then also wrote an algorithm or extracted the proof, extracted from the proof the algorithm for computing some generalized inverses. And the last thing which we did is when the system AX equals to B is solvable, then all the solutions, one of the solutions is GB, where G is any generalized inverse of A. And we were also able to describe all solutions of this system. Now the next task will be to define a special generalized inverse, which will be in fact the generalized inverse because it will be unique with those properties. And from now on, we will only do computations with this more with this specific generalized inverse, because it will also be helpful to solve systems A axis B, which are not solvable exactly, but by means of least squares method. So recall that the last theorem from the last hour was that GB is a solution of the system A axis B if the system is solvable. But if the system is not solvable, then GB is not a solution, and we also don't know if this is a solution by the method of least squares. But this more generalized inverse will in fact do the job also to approximate the solution of the system A axis B. So the next topic is the Moore-Penrose generalized inverse. So the Moore. So these are the authors who first defined and studied this special generalized inverse. So let's just write the definition for the beginning. So we will write it as, for short, we will write it as MP. So the MP inverse, generalized inverse of A, of a matrix A, again with n rows and m columns, is any matrix A plus. Again, it is the number of rows and columns are switched because in particular it is a generalized inverse, is any matrix satisfying the following four conditions. So the first condition is just to say that A plus is in particular a generalized inverse of A. So A plus is a generalized inverse of A, meaning that A plus A is equal to A. Now the second condition is that also the other way is true. So A is a generalized inverse of A plus. So this means that we can switch A plus and A in this first condition, and we get A plus is equal to A plus. And then the other two conditions are more technical. They don't look obvious from 1 and 2. So the square matrix A plus. So this is n times n matrix is symmetric. This means that A plus, if we transpose this matrix, then nothing happens. So it remains the same. It doesn't seem obvious why we would need this condition, but it will be seen from the next theorem that this condition is needed if we want that the Moore-Penrose generalized inverse is really unique. So it will be crucially to use this third and fourth condition, which is just analog of the third one. So it will be crucial to use those two conditions to prove that the generalized, the Moore-Penrose inverse is unique. So in the fourth condition is analog of the third. So the square matrix A plus A, this is M times M matrix, is also symmetric. Meaning that A plus A transposed is just A plus A. So except this condition that A plus must be a generalized inverse of A, we added 3 conditions. So the second condition is that also the other way is true. So A plus and A are mutual generalized inverses to each other, which is not obvious from this equation that if G is a generalized inverse of A, then also A should be a generalized inverse of G. And this is not true in general for every generalized inverse. And except this, also we have some symmetry conditions. So A plus is symmetric and A plus A is also symmetric. And now there are 2 questions, 2 natural questions. When we define something, then we have to ask ourselves, is the object of definition, does the object of definition really exist? So does every matrix A has a Moore-Penrose inverse? It's not obvious from the definition that this should be the case. And if yes, is MP is a MP inverse unique? And I've already told you the answers to both questions in the introduction. So both answers are yes. So the Moore-Penrose inverse unique, and it's in fact the Moore-Penrose inverse. I mean, a Moore-Penrose inverse exists, and it's in fact the Moore-Penrose inverse because it's unique. So let's first state this second fact proposition. The MP inverse A plus of a matrix A is unique. And it's a little bit strange to state first the uniqueness before the existence. So we don't even know that it exists, but we already say that it's unique. And the reason is that we don't need to know how to construct it to prove that it is unique. Why? Because the proof of this proposition only uses those 4 conditions. So playing with these 4 conditions is enough to prove that the Moore-Penrose inverse is unique, even if, so we don't even need to know that it exists. And to spare some time, we won't go into the details of the proof. So the idea is nothing deep, but playing with those 4 conditions in such a way to somehow prove that if we have 2 Moore-Penrose inverses, then they have to coincide. We can write 4 conditions for both candidates, somehow play with those 4 conditions and get that they coincide. Maybe I can just show you a short proof in the handouts, and then you can read it yourself, or try to manipulate those 4 conditions to prove that the Moore-Penrose inverse is unique. So it's on this slide. So you see, we start with assuming that there are two Moore-Penrose inverses, M1 and M2. And we would like to conclude that they coincide. So in the last line, we do some calculations and get that M1 is equal to M2. And the proof consists of proving two things. So we first prove that AM1 is equal to AM2. This is the first part. And then by an analogy, we prove that even if we put M1 and M2 on the other side, so M1A is equal to M2A. And once we establish these two properties, it's just one line proof that M1 coincides with M2. So we have M1 is by definition M1A M1. And then we can replace this M1 by M2 because we have AM1 is AM2. So AM1 is equal to AM2. We can do the same for the first M1 because we have this M1 is equal to M2A. So we replace M1 by M2. And now again, by the definition of a generalized inverse of M2, this is just M2. So crucially, we need to prove two things, that AM1 is AM2 and M1A is M2A. And to do this, it's just a manipulation of the corresponding properties of the Moore-Penrose inverse. So this property 3 is this symmetric condition, which I've told you before that it's some kind of technical, but it's crucial for the uniqueness. And you can look at this 4 lines by yourself to see that it's really nothing deep. Okay, and in the rest of today's lecture, we will start building this Moore-Penrose inverse of A. So this will be the first crucial step in solving the systems AX equals to B, where the exact solution doesn't exist. So to calculate the Moore-Penrose inverse of A, and then all other steps will be just computations. Before we start constructing Moore-Penrose inverse, only a few remarks. So the first remark is that if A is invertible, then A plus is just inverse of A. It's really easy to check that inverse of A satisfies the 4 conditions in the definition of Moore-Penrose inverse. So this is the first remark. Then the second remark is that A plus plus is just A. So if you have a square invertible matrix that inverse and then invert, so if we invert and then invert again, we get the initial matrix again. And for taking Moore-Penrose inverses, it's the same. So if we take 2 Moore-Penrose inverses, then we finish with the initial matrix. And it's really easy to see this from the definitions, because the definition of the Moore-Penrose inverse are symmetric in A and A plus. So this condition, the first condition, if we replace A with A plus in the first condition, we just get the second condition. And the same is for third and fourth condition. So this definition is really symmetric in A and A plus, meaning that A plus plus is A. Okay. And then the third remark, which will be also frequently used, is that A transpose. So taking the Moore-Penrose inverse of the A transpose is again the same as taking the transpose of the Moore-Penrose inverse. So if you recall again from the square invertible case, then if we invert transpose of a matrix, it's the same to transposing the inverse. And Moore-Penrose inverse has the same properties. And again, it's easy to see this. What we have to do is just taking the transpose of all of the conditions. So if you take the transpose of the first conditions, I can write it here. So if we transpose the first conditions, we get A transpose, A plus transpose, and A transpose, and this is equal to A transpose. So A plus transpose is a candidate for a Moore-Penrose inverse of A transpose. And if we transpose the second condition, we get the second condition in the Moore-Penrose inverse of A transpose, and the same for the third and the fourth. So only transposing those four equations gives us Moore-Penrose inverse of A transpose. So this is what we'll frequently use, the second and third condition. Okay, and now let's start the construction of the Moore-Penrose inverse. We will start with three special cases, because if we know that the matrix satisfies one of those three cases, then it's easier to just calculate the Moore-Penrose inverse by the construction we will shortly show. And it will also give us an idea how to calculate the Moore-Penrose inverse of a general matrix A. But calculation of the general Moore-Penrose inverse will require singular value decomposition of A. And if possible, we don't want to calculate the whole singular value decomposition, because it requires calculating eigenvalues. And probably you know that if we have big matrices, then calculating eigenvalues is a hard task. So if possible, we would like to calculate the Moore-Penrose inverse without CVD decomposition. And this will be possible in the following three cases. So case one, A transpose A, this is a M times N M matrix, so is invertible. In particular, this means that M must be smaller than N, because rank of A transpose A is at most rank of A. And if N was smaller than M, then rank of A would be at most N. So we know that if A transpose A is invertible, then M must be smaller or equal to N. And now I claim, again, we can think of the invertible case. So if A was invertible, then what we could do is that A minus 1 is equal to A transpose A minus 1. So this would be A minus 1 times A transpose minus 1, because inverting, so if we have inverse of the product, this is just the product of inverses. So inverting changes the the order of multiplication. So what we would need here to get A inverse, so A transpose A inverse, this is A inverse times A transpose A inverse. So what would we need here to get A inverse? So here, so do you see? Does anybody see what we need here to get A inverse? So we have A inverse times A transpose inverse. So we have to get rid of this A transpose inverse. What we need is just A transpose. So here times A transpose, and then this would be identity. So this is in the invertible case. And this is the idea for the claim. Therefore, claim A plus is just, so we replace inverse with the Moore-Penrose inverse. So A transpose A inverse times A transpose. So what does this case one say? If A transpose A is invertible, then the Moore-Penrose inverse of A is just inverse of A transpose A times A transpose. And here we see the idea how to, so here we see the idea how to get this conjecture. So this is the idea for the conjecture below. And now everything is just checking the conditions in the Moore-Penrose inverse. And let's do, for example, first and third condition, and second and fourth are just analogous. So we have to check 1 to 4 in the definition of the MP inverse. And let's do 1 and 3. So A plus A, so A plus A must be A. We plug this candidate for A plus into this expression and get A times A transpose A inverse times A transpose times A. So I'm doing these different parentheses to differ from the parenthesis from the inner parentheses. Otherwise, it's not meant that these are matrices. It's just a different type of parentheses so that the calculation is clearer. And now this is the same as I just get rid of the parentheses. It's A transpose A minus 1, A transpose A. And if I join the last two matrices, I see that I get exactly identity here. So A transpose A inverse times A transpose A is identity. So what remains is A. So the first condition is okay. And then the second is analogous. You can do it yourself. And then the third is to check that A plus is symmetric. And here we will use one of the remarks. So A plus transpose is A transpose plus. So let's calculate this condition. So A plus transpose, we plug in the candidate for A plus, A transpose A inverse, A transpose, transpose everything. And recall that we have here A, B transpose is just B transpose times A transpose. So if we transpose the product of matrices, then we just multiply the product of transposes in the other order. So it's easy calculation. This is one of the basic calculations in linear algebra. So transpose changes the order of multiplication. It's the same as inverting. So if we invert the product of invertible matrices, then we have the product of the inverses in the other direction. So we use this here and get that. So first we have this A transpose transpose. Then we have this A transpose A minus 1 and everything transposed. And the last A transpose. So I transposed all three factors and wrote them in the other order, in the reversed order, since this is what transpose does. And A transpose transpose, this is just A. And here we have A transpose A, A transpose A inverse transpose. So we use that, we can swap minus 1 and transpose. And rewrite A transpose again. But this A transpose A, this is symmetric matrix. So A transpose A, if we transpose, we again get A transpose A. This is symmetric matrix. So this is just A, and I can leave this transpose. We get A transpose A inverse, A transpose, and we are done, because this part is just our candidate for A plus, if you recall. So this is our candidate for A plus, and we got A plus. So we started with AA plus transposed, and we end with AA plus. So this AA plus is really symmetric, and the third condition of the Moore-Penrose inverse is met. And 4 is analogous to 3. So the second condition is analogous to 1. And the fourth condition is analogous computation as the computation in 3. So when we start with the matrix A such that A transpose A is invertible, then this is the easiest way to calculate its Moore-Penrose inverse. So we can compute A transpose A, invert it, and multiply by A transpose. And no need to calculate singular value decomposition of A, because singular value decomposition is computationally very demanding. It requires calculating eigenvalues. Okay, this is the first case. And as you've seen already from the construction above, that all the constructions has also its transposed versions. So case 2 would be that A transpose, if we swap A and A transpose, then we get a n by n matrix. And if this A by n matrix is invertible, then we can do similar as here in case 1. So it's just analog of case 1. So case 2, A transpose, this is n by n matrix. So if this is invertible, meaning in particular that n must be now smaller than m. Now in this case, analogously as in case 1, we can check that A plus is then equal to A transpose A transpose inverse. And again, if A transpose is invertible, no need to calculate the Moore-Penrose inverse, no need to calculate CVD decomposition of A to get the Moore-Penrose inverse of A. Okay, and the last case for today, and then next time we start with a general matrix. So it's case 3, which will also be needed in the general case. So let's assume that sigma is diagonal matrix. You will see next time why I've used this notation sigma. So it's a diagonal n times n matrix is diagonal of the form. Now we have to separate two cases when n is smaller than m and when n is bigger than m. So when n is smaller than m, then we get matrix sigma of this form, sigma 1, sigma 2 on the diagonal, sigma 3, and so on, and sigma m. And since there are more columns than rows, we have here some 0 columns. This is one possibility. And the other possibility is that there are more rows than columns. So in that case, we start with sigmas on the diagonal, and we bump into the right end of the matrix, and then we have some 0 rows below. And those matrices have really nice Moore-Penrose inverses. So it's what you would expect. So then sigma plus is equal to. So in the first case, sorry, just a little bit delay of Zoom. So in the first case, we just swap the number of rows and columns, and we have then sigma 1 plus, sigma 2 plus, and so on, sigma m plus, and some 0 rows below. And in the second case, again, we swap the number of rows and columns, and we get sigma 1 plus, sigma 2 plus, and so on, sigma m plus, and then we have some 0 columns at the end. I see the question in the chat, just that I write this to the end and then I look at it. So what are those sigma 1 pluses? So sigma I plus is equal to, why I didn't write sigma I to the power of -1, because here I didn't assume that those sigmas are all non-zero. So some of them could be also zeros. So that I could handle all in one case, I just wrote sigma 1 up to sigma m, allowed that some of them are zeros. But of course, I cannot invert zeros. That's why I wrote here sigma I plus, and it is just 1 over sigma I if sigma I is non-zero. Otherwise, it's 0 if sigma I is equal to 0. So this is the only reason why I used pluses instead of usual minus ones. So usual inverting of real numbers. Okay, now I look at the chat. The last sigma n in the second case. Let's look. So sigma n. So the first has n rows. In fact, yeah, if we are strict, yeah, I made here mistake. So it should be in the first case. Thank you for this observation. In the first case, because n is the number of rows, it should be here n, and yeah, here m is the number of columns. So in the second case, it's okay, and here then inverses also. The first should have here n. So here n, and here it's okay. Yeah, thank you for this observation. Yeah, so I didn't use the fact that sigma has n rows. Okay, this is all for today. I stop recording.